All right, so here we go. We're picking back up with the low-resolution ladybugs. Yesterday, the farmer was trying to maximize the area for his 500 linear inches of fencing, and we came up with what Colin said was a square, a 125 by 250 rectangle. Okay, so now we're going to talk about the same ladybug farmer, but now he's kind of upping his little ladybug operation here. He has purchased some expensive, extraordinary diva ladybugs who require, this is what makes them divas, they require exactly 10,000 square inches of grazing in order to be at their optimal ladybug-like state. Okay, you got to give divas what they demand. What is the least amount of fencing? He's gonna be willing to go invest in whatever fencing he needs to cover exactly 10,000 square inches of grazing. So what's the least amount of fencing that he could buy in order to accomplish that goal? And he is still not required to build along the river, and he is still clipping their wings. Okay, so they still can't fly. So let's draw a picture again, and we'll use blue for the water. Makes sense. And for the fencing, I'll use purple for the fencing this time. And inside there we have green grazing area. All right. So now we got to label the unknown parts. I don't know what we used yesterday, but I'll use L and W today, just to show you that it really doesn't matter. Now we're going to write an equation for what it is we're trying to optimize. We're trying to maximize or minimize what? Very good. We're trying to minimize not the area, the amount of fencing, the perimeter, in essence the perimeter, minus the water. So we're trying to minimize the perimeter. I'll just put minimize fencing. So we're kind of flipping the previous question on its head. So let's call it F for fencing, or whatever you prefer to use, capital F. And the fencing is going to be 2W plus 1L, correct? 2W plus 1L. What? What? Well, that was when we were trying to maximize area. Here we're trying to minimize perimeter. All right, do it your way. Let's see. Do it your way. We'll see. We'll see. And then we'll publish it. We'll publish a work together. All right. All right, so now what is the constraint? The area, 10,000. Good. So 10,000 equals L times W. There's your constraint or limiting condition. You want to solve 10,000 LW for L or W? You solve it for W. I'm going to solve it for L. Okay? It's just as easy to solve for either one of them. But again, we don't want to get into the barely legal level of fun by having to plug in a W and then double it. So I'm just going to solve that for L and plug it in right here. So the amount of fencing then in terms of just the W is 2W plus 10,000 over W. And now we'll kind of list our relevant domain. What do we know about W? It's got to be positive, right? Some positive number. Of course, it could be less than something. It could be less than maybe the square root of 10,000. But that's not really critical. We just know it has to be a positive number. So we're looking for the values that make the derivative 0 for values of W greater than 0. So if you want to rewrite this so that you could take the derivative without careless mistakes, W to the negative first. Unless you were going to use the Hody-High rule, then I apologize. All right, so F prime is going to be 2 minus 10,000 W to the negative second. And remember then, we're trying to get a single, a single fraction. So let's go ahead and instead of factoring out least powers, let's just do it the other way. If you take the W squared to the bottom, think of this as being 2 over 1. Just multiply the first one by W squared over W squared, right? Bless you. You get a common denominator. And so you get F prime would equal 2W squared minus 10,000 all over W squared. And I guess you could even factor that out if you want. I don't think I'm going to. We want to know where that's equal to 0 now, because the values that make the derivative undefined are typically not even physically possible. So f prime is going to equal 0. We'll show that when the numerator, 2w squared minus 10,000, equals 0. And now we solve this little handsome quadratic, and you get w squared equals half of 10,000, which is 5,000. And if you take the square root of that, I'm running out of room. Oh well. W is going to equal, now plus or minus, do we want the negative one? Does it make sense? No. So we'll just take the square root of 5,000. And that probably simplifies to something, right? Can we simplify that? I know 100 is a factor, and 100 is a perfect square, so that'd be 100 times 50. So the square root of 100 is 10. 50 is 25 times 2, so I can pull another 5 out, and I'm left with just a 2 inside the radical. So 50 square root of 2. 50 square root of 2. So that's going to be the only critical value that emerged in a situation where the endpoints don't make sense because they collapse the structure down to nothing. So can I assume that that's my answer? Yeah, for the most part, you can. And if you wanted to verify it, you can do one of those modified first derivative tests or second derivative tests and show that it's an absolute extrema, or a value that minimizes the fencing. We should probably do that. Let's do the second derivative again. Okay? I just want to talk about justifying, because it is kind of an important idea. If that's f prime, rather than plugging values on either side, let's just take the derivative of f prime to get f double prime. The 2 goes away, and we're left with 2 times 10,000, which is 20,000, w to the negative third, which is over w cubed. So if that's the second derivative, notice the sign of the f double prime is determined by the sign of w. What types of w's are we using? Positive. So here's what you would say. F double prime is going to be greater than 0 for all w greater than 0. And so that means our function for the fencing is concave up. It's positive, so it's concave up for all x in that interval. So it's not just a local min, it is an absolute min. So this upside down a, the for all, that makes it the global argument. Okay, that makes it the global argument. So now you can say, so 50 square root of 2 inches minimizes. And if you want to add the adverb in there, absolutely, the fencing. You're not always going to have to justify. In fact, very infrequently are you going to have to justify, but it's nice to kind of know how you would justify it, or just to make sure that you're finding the minimal quantity. All right, so now we answer the question. Did he want the dimensions of the pin, or did he want the amount of fencing? What did it say? What is the least amount of fencing? So we actually want the fencing now. So he knows what to go by. So now you take that. We have a fencing equation right here that's strictly in terms of w. If you want to know the dimensions, here is the other length in terms of w. So again, there's a couple of quantities that are related to the optimal quantity. So let's answer the question. So he needs at least 2 times w. That's going to be 2 times 50 square root of 2 plus 10,000 all over 50 square root of 2. I'm just literally plugging it in right there. Inches of fencing. Now, even if he went to like the Ladybug Emporium, where they cut the fencing to length, so you don't have to buy like a roll that has extra, they'll cut it exactly to length that you need. He's not going to be able to get it cut to the exact length. Why? Yeah, square root of 2 is an irrational number, so it doesn't have a place on the number line. So should he go to the first number that's rational below that or over that? over that. Because if he gets a little bit too little of fencing and he leaves just then the smallest amount of space open from that lack of fencing, guess who's going to squeeze through there? Those tiny ladybugs. And he doesn't want to have to learn that lesson the hard way. All right. Okay, cool. Any questions on that? Yeah, that number simplifies, and if you want to do that, that's fine. But I think you got the idea. So optimization, not hard, right? Kind of fun? Not hard, kind of fun. Good. Pretty fun, not hard at all. Kind of fun. All right, example 5. It says for example 5, sometimes the endpoints are relative. So up to now, the endpoints haven't really made any sense. So the geometric cases, when you go to the extremes on the endpoints, they collapse your structure down to nothing in either dimension on the two extremes. Sometimes, though, as it says, the endpoints are relevant, and therefore they could be the optimal value by the EVT. Here's one of the times where they do show up as relevant. When you're trying to find a point that is closest to another point on a curve. Okay? These are distance questions. Find the point on the graph of y equals x squared that's closest to the point 3, 0. Can we draw a picture for this one? Yeah, we can. We can get the graph of x squared. So let's go ahead and do that just to orient ourselves. Looks something like that. There's y equals x squared. And we want to find a point on that graph that's closest to the point 3, 0. So I'm going to say 3, 0 is right here. Now 3, 0 is not on the curve, right? Thank goodness. If it were on the curve, then it would be closest to itself. All right, so now let's take a look. Let's see where the winning points could be. It could be the origin, right? How far away is the origin from that point? 3 units. We already know that just by looking at it. And it could be the value that's straight up from there. Maybe that point's the one that's closest to it. How far away is that? What's the y value there? 9. 3 squared is 9. So based upon that, we know that this point here is not going to be the closest point, because already the origin is closer by a factor of 3. Might it be a point to the right of 3? Could this point then have a chance at being the closest point? No. Once you get past x equals 3, which is the vertical line, those points are just going to be further away and greater than 9. You can tell that. Might it be a point then to the left of 0? Could this point over here be the closest one? No. By the same reasoning, if you go to the left of 0, that distance is going to be greater than 3, so it's not even going to be a candidate. So notice if you're looking at x values, you know then that the winning or the closest point could be 0 at x equals 0, or at 9, which we've already said it's not, or any point in between. So in this case, the endpoints are relevant. They're not dimensions of a geometric shape that collapse down to nothing. They are possible locations where the point is closer. But we also want to make sure that we include everything in between there on the graph. So this could be just a random point, x, y, that is actually closer. All right, so we know it's an optimization question because it says closest, and that's the superlative case. But what is it that we're trying to optimize? Are we trying to maximize closeness? Minimize distance, right. You actually maximize closeness by minimizing distance. So let's go ahead and say that. We're going to minimize the distance. All right, so what you want to probably do is just draw a generic picture from an arbitrary point x, y to the point 3, 0. So here are the 2 points that I have, x, y, and 3, 0. We're going to write the equation then for the quantity we're trying to minimize. That's distance. What do you want to use for distance? Big D? I would recommend big D, not little d. Big D. And, of course, the distance formula is the square root of the change in x squared plus the change in y squared. You remember that from little school? All right, so let's go ahead and plug in. The change in my x's is going to be, I'll do x minus 3 squared, plus the change in the y's, I'll do y minus 0 squared. So there's my primary equation. Notice it is in terms of 2 variables, x and y. I want to be able to write the distance as a function of either x or y. What's my constraint? What's preventing me from getting right up there in 3-0 space and saying, is this close enough for you? It's got to stay on the graph of the parabola. So what is an equation that relates x to y on the parabola? Y equals x squared. Holy moly. The secondary equation was given to us. I'll just write it again, just to feel like I'm doing something. You want to solve that for y or x? It's already solved for y. The problem is practically doing itself at this point. All right, so I'm going to plug that in for y. But first I'm going to simplify this. X minus 3 squared, that's plus y squared, right? If you simplify, y squared is going to be x squared squared. So that's now what we're trying to do. And our x values, as we already said, have to fall between 0 and 3. Endpoints make sense now. In fact, we already know the distances at 0 and 3, don't we? Just from looking at the graph, vertically and horizontally. We got to take the derivative of this. So we have some things to consider now. We can leave it factored under the radical or expand it out, whatever you prefer. You want to expand it? Okay, let's expand it. So I get the distance is square multiplied by square. You get x squared minus 6x plus 9 plus x to the 4th. Sweet. Now I have a polynomial under a radical. So if you do the distance derivative, you get d prime. Well, that's going to be all that to the 1/2 power, right? So it's going to be 1/2 blob to the negative 1/2. And I'll just rewrite that for what it's worth. Times the chain rule. That's what we're really after, because this is going to be in the numerator. The derivative of that is 2x minus 6 plus 4x cubed. So that's why we expanded it, so that we could take the derivative of that a little bit easier. All right, if I clean that up, then d prime is going to equal, notice I could do something here, and y'all are BC, so I know you'll be able to follow me along with it. I could factor a 2 out of each of these three terms and divide it out with that 1/2. So in the denominator, I'm going to have the square root of all of that stupid stuff, x squared minus 6x plus 9 plus x to the 4th. We're not interested in where the derivative is undefined for these optimization problems. We just want to know where it's equal to 0, which now in the numerator, if I write it in descending order, it's 2x cubed plus x minus 3. And if I set that equal to 0 now, that's going to equal 0 when 2x cubed plus x minus 3 equals 0. And all I got to do is solve it. I don't have a calculator. It's a cubic trinomial. Does it factor? No. Not very easily. But here's what we do know. We do know from pre-cal that if I can find at least one root of this, I can synthetically divide it out and get down to the quadratic, which then I'm home free. So if you are given something like this, one of the solutions can be found by guess and check. It's going to be a relatively nice number. You said we already know one? We already know one? 3? 3 works? 3 cubed is 27. 27 times 2 is 54. 54 plus 3 is 57. 57 minus 3 is 0. Actually, it's kind of, we know, we actually don't know one of these, but we could do guess and check. If you're going to be doing guess and check, I would say start with 0. Does 0 work? Nope. Try 1 or negative 1. 1 works here, right? If you plug in a 1, you know you get 2 plus 1 is 3. 3 minus 3 is 0. So I know that's going to factor as x minus 1 times something. So guess and check is actually viable. Well, if you're stranded on an island and you absolutely need a root, you're going to be like, oh, well, I don't know the cubic formula. I guess I'll live here forever and just starve to death. No. You do what you need to do. You do trial and error. And at least now you have one of the factors. You still may starve to death because you're on an island, but you're going to be happier. What's the other factor? It could be food, right? Synthetic division, very good. I know that's what you were thinking. So 2x cubed, 0x squared, 1x, and minus 3. That looks like some kind of bizarro 2013 date. Like the Zodiac Killer or something. I don't know. Let's bring down the 2. Oops, not like that. Bring it down like that. Multiply. We did this with limits, right? We did synthetic division, so we know how to do this. You get a 2, multiply, you get 2. 2 plus 1 is 3. 3 times 1 is 3, and you get 0. So the other factor is 2x squared plus 2x plus 3 equals 0. We're using a lot of math here from our math career. Now the quadratic might factor, right? Maybe, possibly maybe. Factors of 2 and 3 that add up to 2, I don't think I'm going to be able to find them. So here's where I can go to the handy-dandy quadratic formula, which we do know. So let's see if that works. X equals, remember it's the opposite of b. b in this case is 2, so that's negative 2. Plus or minus b squared, be careful, that's 4. Minus 4 times a, which is 2, times b, which is 3, all over 2a, which is 2. Look at the discriminant. Remember that word? Ooh, the discriminant. What type of number do you get under the radical? 4 times 2 is 8. 8 times 3 is 24. 4 minus 24 is negative. That means that the only remaining solutions are imaginary. Okay, so there's no other solutions that are real. The only real solution was the one we found by guess and check. X equals 1. So I'll go ahead and say right here, x equals 1. Now, is x equals 1 in our relevant domain? Yeah, it's between 0 and 3. Now, in this case, you only got one critical value. That one is not guaranteed to be the answer, like it has been in the geometrics. We actually have to figure out what the closest one is. It's going to be one of the 3. So let's go ahead and do the EVT version. We want the distance at 0, the distance at 1, and now the distance at 3. Well, we already know 2 of those, right? The distance when x is 0 was 3. The distance when x was 3 was 9. Now, if you weren't sure, you could actually get that same information by plugging it into either one of these guys. And you'll get the same answer, okay? But I'm not going to plug in more than I have to. So let's go ahead and plug in the 1. I think I'm going to plug it into the expanded version, maybe? You want to plug it into that one? Into x squared? Can you plug it into x squared? Well, that'll give you the y value there, but then you'll still have to figure out the distance between that point and that point. Yeah, which is what this is already set up to do. So let's go ahead and plug in a 1. We'll do it together. 1 minus 6 is negative 5. Negative 5 plus 9 is positive 4. 4 plus 1 is 5. So we get the square root of 5. Square root of 5. Now, by the EVT, one of these has got to be the biggest, and one of these got to be the smallest. 9 is looking like he's going to be the farthest away on this interval. The square root of 5 is about what? It's 2 point something, right? Which is less than 3. So it turned out that the point that was closest to it was the critical value point, but that's not always the case. So you have to check. All right, so now we'll answer the question. And by the way, this is your justification. If you ever had to justify on a closed interval, this is your justification. It said to find the point on the curve. So the closest point is 1 comma, that's how we find the y value. Yeah, you plug it in there, and you get 1. The distance happens to be the square root of 5. No. No, the graph is never justification. Your justification when you have endpoints is this. This is your closed interval argument. You don't have to use a modified global argument for a max or a min. That's the justification. All right, so there you go. Let's see when the endpoint could be the answer. Let's say you had a parabola that opened downward, but it opened pretty wide. And we were trying to find the point that was closest to this point here. You could probably just reason by looking at it that the point that's going to be closest to it, bless you, is 0, right? Which would be an endpoint of some kind of interval. If the point was, instead of outside, what if it was on the inside, like right here? Maybe that's the closest point, maybe that's the closest point, or maybe it's something in between there. You can kind of tell that if this parabola was open wider and that point was closer to the vertex, it would look like the vertex, which would be the end point, would be closer than any of the others. Okay? Same thing if it opened very, very narrowly and you had a point like right here or something. It looks like the end point on the right would be closer than anything else. So the endpoints, whenever it's one of those minimizing distance questions, the endpoints are meaningful. So just kind of keep that in mind. All right, so here's just kind of a summary of what we've been doing. The way to justify an absolute extrema. If this shows up as a free response or on one of my quizzes and I ask you to justify, the closed interval argument is used when you have endpoints, and that's exactly what we just did right here. So if you can compute the quantities at your endpoints and at the critical values that you find and show the work for, that's the justification right there. You just say so, and you answer the question. The other way, and I'll just jump down here to the other box, is the modified first derivative test. That's the one we did in the very beginning with the numbers. That's the one where you have to say that, let's say x equals 5 is the absolute maximum location since the derivative is greater than 0 for all values to the left, and less than 0, for all values to the right. And then, of course, the modified second derivative test, where you say that the graph is either concave up or concave down for all values in the interval. And that's what we just did on this ladybug problem. So anyway, the key words on the global arguments are for all, or, of course, the upside down A symbol in your relevant domain. So that's why for optimization, it's important to find that relevant domain. You're looking for the global extrema on that relevant domain. All right, example 6. Find the point on the curve cosine of x closest to the origin 0, 0. Is this one of those closest to questions again? Yep. So are the endpoints going to be meaningful and relevant? Yeah. All right, step 1, let's draw the curve, cosine of x. Cosine of x is chala. So looks something like that. And then we'll draw a little bit over here. This goes up to 1. This goes down to -1. And we're trying to find the point that's closest to the origin, right there. So immediately, just from the graph, you can kind of get an interval already. It looks like straight up, when x is 0, we already know the distance to be 1, don't we? And if you go straight to the right, that first x-intercept is at what? Pi halves. So that distance is pi halves. If it goes to the right of pi halves, I can already tell that that line is going to be longer, so it's not going to be to the right of pi halves. But if there is one on the interior right here at xy, I know that there's going to be another one over here by symmetry, right? So in this case, you could just work in the first quadrant and know that if there's one that exists in the first quadrant, there's going to be a one over there that's symmetric to it. You would have to name both of them, yeah, if it ended up being on the interior. All right, so let's go ahead and do what we did before. We have the origin, which is 0, 0. We have the point xy. We're trying to minimize the distance. So the distance formula is the square root of, we'll go straight to it, x minus 0 squared is just x squared, plus y minus 0 squared is y squared. So there's our primary equation. Now I need to relate x to y. How do I do that? Y is equal to cosine of x. Sweet. So, okay. So I get the square root of x squared plus cosine squared of x. And what's my relevant domain now that I have it in terms of one variable? Between 0 and pi halves. Okay, so same thing. Take the derivative. Here we go. D prime is 1/2 blob to the -1/2. We really don't even care about that part right now because it's just going to jump downstairs and we want to know where it's going to be equal to 0. So here's the part that matters. Times the chain rule. The derivative of x squared is 2x, plus the derivative of cosine squared is the chain rule, right? It's 2 times cosine of x to the first power times the derivative of cosine, which is negative sine. Okay, that's cosine of x to the first times that. So if you want to show it like that. All right, so now we clean that up like we did before. And also like we did before, that 1/2 can actually divide out with that 2 right there. So in the numerator, we're going to be left with an x minus sine x cosine x all over the square root of x squared plus cosine squared of x. And there's a cleaned up version. Now we want to know where it's equal to 0. So that's going to be when x minus sine x cosine x is equal to 0. How are we going to solve that one? That one's not as easy to solve without a calculator. Are you okay with that, Colin? You see what I did? This piece is in the numerator, factored out the 2, and then the negative comes out front. All right, so this one, if you're expected to find critical values on something like this one would end up being a calculator question. So if you have a calculator and you want to get it out, that's fine. If not, I'll just kind of show you the keystrokes here on the classroom demonstrator version. What mode should we be in anytime we're graphing sine or cosine or tangents? Radians. Let me check that first. Whoo! I was in degree mode. Good thing I checked. All right, now I'm in radian mode. So I'll type it in very carefully. X minus sine of x, close parentheses, cosine of x, close parentheses, and now I want to know where it's equal to 0. And now the window that I'm in, I set my window to 0 on the bottom, pi halves on the top. And since I'm looking for the x-intercept, -1 to 600,000 is probably not good. I'll go -3 to 3. Again, that keeps the x-axis in the middle and kind of stretches out the graph a little bit. And I always keep my scales at 0. So there's the graph. There's the point of intersection. Sweet. Let's try intersection. I don't know. Second trace, number 5. Enter, enter, enter. Error, no sign change. What does that mean? Yeah, it actually doesn't. See, right in here, it looks like maybe it crosses in there. It's too close to the x-axis. So if you want to really stretch out the vertical window, how about -0.1 to +0.1? That really stretches it out. If you keep doing that and zooming in right here, you're going to see something that looks like this. You're going to see it. One of them is going to look like that, and the other one's going to grow straight out of there. So they never intersect on the interval. So what does that mean? How many critical values do we have? There are no critical values. Oh, so in this case, not only are the endpoints relevant, they're the only ones that we have. And since we already know the two distances, we don't have to plug it into this formula. We can just look at it up here and now ask ourselves which one's closer, when the distance is 1 or when the distance is greater than 1. 1, yeah. So the closest point is what? Yeah, on the graph it would be 0, 1. Yeah. It's the local maximum. Had it been pi halves, 0, then there would have been a symmetrical one over here at -pi halves, 0. No critical values on that interval. Sweet. All right. Any comments or questions on that one? All right. Example 7. This one makes a good quiz question. Like the last 3 years, this is the one I've used as a quiz. Find the dimensions of the largest rectangle that can be inscribed under the curve of that in the first quadrant. Anyone for drawing a picture? Yes, please. All right. So we've got the graph of 16 minus x squared. That's going to have a y-intercept of 16. and it's going to open down on both sides. You can probably figure out without too much effort what the x-intercepts are, right? If you set it equal to 0, you get 4 and negative 4. So we're working in the first quadrant. So we're working in this region right here. I want to know what the largest rectangle is that I can squeeze underneath there. That is one with the most amount of area. Is this going to be the winner? Is that going to be the winner? It's going to be you and your squares. You think it's going to be a square? Certainly this one is not going to be the winner, right? Because I still see space on all four sides. So I know that I can make it bigger. The winning candidate, believe it or not, to maximize the room, it's going to have two of its sides on the axes themselves. It's going to press up against that right angle. And then the corner, I'll just leave it like that. All right, the corner is going to be on the graph, x comma y. Now the winning candidate, it may be like a tall drink of water like that, or a stubby short guy like that, or anything in between. So instead of drawing a bunch of different rectangles, you just draw a representative rectangle, okay, somewhere in the middle. Now we want to label the sides, but I don't want to use L and W or A and B here because I'm on the coordinate grid. So I'm going to call the width X, and I'm going to call the height Y. Why would I do that? Very good. Because that's the point XY right there. Go over X, go up Y. So now I'm trying to maximize the area. So I'm going to use A for area. What would be the area of that rectangular rectangle? XY. Sweet. YX. Now we got to get it in terms of a single variable. What's the constraint here? I can't go outside of that, so I'm limited by the curve itself. The curve then is already solved for y, so I'll leave it solved for y, and I'll plug that in right here. So I get A equals x times 16 minus x squared. And now I can come up with a reasonable window for x. What's the smallest x could be? 0. And in this case, it can actually equal 0. You can actually let x equal 0. But if you do that, you've collapsed the width down to nothing. What would be the maximum x could be? 4. And if you do that, you've collapsed the height down to nothing. So closed interval here would work, but you already know then that the endpoints are going to be absolute minimums, not absolute maximums. Which means on our relevant domain, if we had a 0 here and a 4 here, we know it's going to be 0 at 0 and 0 at 4 because we've collapsed it down. And because I know they're positive areas somewhere in between, I know for a fact then that on that interval, I'm going to have a critical value that will give me the absolute maximum on that interval, even though the area is a cubic function. So let's go ahead and expand it, 16x minus x cubed, and take the derivative. So we get 16 minus 3x squared. If I then set that equal to 0, you get 3x squared equals 16. So x would equal plus or minus. Do I want the minus in this case? No, because I'm only working in quadrant 1. So it's just going to be positive square root of 16/3. And I'll leave it like that. That has to be the answer. That's the value of x that maximizes the area because of what I know the graph of the area to look like. Now I answer the question. It said to find the dimensions. So let's do that. So the dimensions. Do we have units in this problem? No, there's no units. So the dimensions are, does it matter which one I'm calling x and which one I'm calling y? Yeah, it does. So I'm just going to say our x equals the square root of 16/3 and y equals, I need to find y. So I'm going to plug it back into the parabola equation. So that would be 16 minus 16/3 squared would just be 16/3. And I'll leave it like that. If you want to come up with a simplified version, feel free. So that's a pretty easy one. Pretty straightforward. Modifications of this. What if I was trying to find the largest rectangle that could be inscribed under the parabola still, but in quadrants 1 and 2. Yeah, you could just extend it out over here, and now your area is not going to be x times y, but 2x times y. And then it works out to be very, very similar. Okay? So, not saying y'all are going to have a quiz like that tomorrow, but I've done it the last 2 or 3 years, so we'll see. Did I say tomorrow? I think I did. Yeah. I don't want to give you a quiz right now. Yeah, because I was looking for the dimensions, that's x times y. So here's the x. I plug it in there to get y. If we wanted to know the actual area, here's the equation right here, either one of these two that gives you the area in terms of x. So you'll always have like 2 equations to find 2 different values. You just have to answer the question by plugging it into the correct one. Okay? Alrighty. So if you want to read that, those are the steps to a successful optimization problem. I'll just point out the last one. Smile. Okay. All right, let's jump to, let's see, we got it. Okay, we're making good time. Example 8. An open top box. Ooh, those are my favorite kind. You don't have to mess with the lid or anything. Just put stuff right in it. An open top box is to be constructed from a square piece of cardboard. There's your square, Colin. 3 feet wide. The cardboard's 3 feet wide by 3 feet wide. We're going to cut out a square, another square from each corner, and we're going to bend up the sides. What's the largest volume the box can have? This is like the most classic optimization problem in the history of optimization problems. You open any calculus textbook under the optimization section, you'll see this problem in there. So, kind of boring, but I feel like we have to do it. All right, so here is our square piece of material with which we're starting. It's 3 feet by 3 feet, okay? 3 feet by 3 feet. We are going to construct it by cutting squares out of the corners and then removing these pieces here. And then you can imagine like dotted lines here on the folding lines. If you fold it up along those lines, you'll end up with a box that looks something like this. Okay, and maybe you'll put like sticky tape here to keep the sides up. I don't know. Okay, but there you go. You got it? Sticky tape works better than unsticky tape. It sticks better. All right, so let's go ahead and write an equation for what it is we're trying to optimize. We're trying to find the largest volume, so we're trying to maximize volume. I'm going to call the equation V for volume. What is the volume of a rectangular prism? Length times width times height. Oh boy. That's in terms of 3 unknowns. We need to get it in terms of 1 unknown. Either L or W or H or some third-party variable. Fourth-party variable. What? Why? Okay, square. All right, good. So we know that. Good. But let's go ahead and define our variable. If we're going to be cutting something out of each corner and we don't know what that value is, I'm going to call it x. So let's say we cut an x by x square from each corner. Are you okay with x? Okay. So now when I fold it up, I want to be able to write these dimensions in terms of x. So if it was 3 feet all the way across, what is that going to be? Because that's going to be like the length. 3 minus 2x. Good, because we took an x from each corner. And as the square boys in the back already noted, that's also going to be 3 minus 2x. All right? And what's the height going to be? When you fold it up, the height's going to be just x, right? So instead of in terms of LW or H, we'll write it all in terms of x. So we're going to have a height of x, and then a 3 minus 2x times a 3 minus 2x, or a 3 minus 2x quantity squared. Okay? Now we could think of a reasonable domain for x. Can we cut 0 from both sides? Can we cut 0? Physically, it's possible to not cut anything, right? So it's possible. So I'll put a bracket there. But I know that if I don't cut anything, I don't have volume at all. I just have my cardboard. That's still flat. The height is 0, so the volume is going to be 0. That's going to be an absolute min. What would be the largest I could cut out of both sides of a 3-foot by 3-foot cardboard? 3/2, good. I'm cutting X out of both sides. So I'm going to put a bracket there because I could do it. Just wait and watch me on a rainy day. I'll do it. You just cut 1.5 feet from each side, and what have you done then? You've obliterated the cardboard, and you have nothing left with which to make the box. So I know that's also going to be a minimum. I get a minimum value of 0 and I cut out nothing. I get a minimum value of 0 and I obliterate the cardboard. So somewhere in between a 0 and a 0 has to be some positive number. And just like we said right here, it's going to be at the critical value. All right. So now we need to find it. Product rule? Expanded power rule? What do you want to do? Okay, I'm going to just go ahead and use the product rule. You expand it, and again, we'll compare answers. The derivative of x is 1 times the second goes along for the ride. Plus x goes along for the ride times the chain rule, 2 blob to the first power times the chain rule. The derivative of the blob is -2. Done. Now, this is already partially factored. Remember, ultimately, we want it to be factored because we're going to set it equal to 0. That's why I chose to do it this way. It was factored to begin with. So now you can, I'll set it equal to 0 right here, so I don't have to worry about v equals anymore. And I'll factor out the 3 minus 2x, and then I'll go with the beefy brown bracket. Oh, thank you. I'm left with a 3 minus 2x, and in the second one I'm left with a minus 4x, correct? Because I took the entire 3 minus 2x away. It's still equal to 0, so I get 3 minus 2x, and in here I get 3 minus 6x. So now if I set them each equal to 0, I get 3 equals 2x, and x equals 3/2, or 3 equals 6x, and x equals 3/6, or 1/2. Are both of those in my relevant domain? Yeah, 3/2 is the endpoint, which I know is going to give me a minimum volume of 0, because I destroy the cardboard. 1/2 then is the only critical value on the interior, and because I know the volume at both endpoints is 0, I know that 1/2 has to be the answer. So that is the answer. We're measuring in feet. So here's, what does it say? What is the largest volume? So now answering the question is getting the volume. Here is the volume equation strictly in terms of x. So the max volume is...
Good morning, Unicorns. Happy Thursday. If you guys can please take a stand for the Pledge of Allegiance. I pledge allegiance to the flag of the
United States of America, which stands
one nation,
under God, indivisible, with liberty and justice for all.
honor and
Justice for all. I pledge allegiance to the United States and one state, under God, one indivisible.
ladies and gentlemen, please remain.
So the maximum volume is 2 cubic feet.